We stand on the brink of a new technological revolution. This revolution promises to transform the very fabric of our society, altering how we live, work, and interact with the world around us. This revolution is driven by our growing understanding of the quantum world. Quantum mechanics, a field that once seemed purely theoretical, is now paving the way for groundbreaking advancements in computing technology. This is the realm of atoms and photons, where the rules of classical physics no longer apply. Here, particles can exist in multiple states at once, and they can be entangled over vast distances, behaving in ways that defy our everyday experiences. In this strange and wonderful domain, we find the potential for a new kind of computer, one with the power to reshape our world. Quantum computers harness the peculiar properties of quantum mechanics to perform computations that are currently impossible for classical computers. Imagine a computer that can solve problems in minutes, problems that would take classical computers billions of years to crack. This is not science fiction, it is the promise of quantum computing. Classical computers, which have served us well for decades, are reaching their limits. They process information in binary bits which can be either 0 or 1. Quantum computers, on the other hand, use quantum bits, or qubits, which can be both 0 and 1 simultaneously, thanks to a property called superposition. This is the promise of quantum computing. By leveraging superposition and entanglement, quantum computers can explore a vast number of possible solutions at once, making them exponentially more powerful for certain types of problems. It's a fundamentally different approach to processing information, one that leverages the bizarre laws of quantum mechanics to perform calculations in ways we never thought possible. This new paradigm opens up a world of possibilities that were previously unimaginable, one that leverages the bizarre laws of quantum mechanics to perform calculations in ways we never thought possible. Quantum algorithms, such as Shor's algorithm for factoring large numbers, demonstrate the potential to revolutionize fields like cryptography, where classical methods fall short. This is not just about faster computers, it's about tackling problems that are completely beyond our current capabilities. From developing life-saving drugs to designing new materials and revolutionizing artificial intelligence, quantum computing holds the key to unlocking a future of unprecedented possibilities. Imagine being able to simulate complex molecular interactions with unparalleled accuracy, leading to the discovery of new medications and treatments. Or envision creating materials with properties tailored to specific needs, revolutionizing industries from aerospace to energy. Quantum computing holds the key to unlocking a future of unprecedented possibilities. The potential applications are vast and varied, limited only by our imagination and our ability to harness this powerful technology. But this journey into the quantum realm is not without its challenges. Building stable quantum computers is a monumental task. Qubits are incredibly delicate and can be easily disturbed by their environment, leading to errors in calculations. Building stable quantum computers is a monumental task. It requires maintaining qubits in a state of coherence, where they can perform calculations without being disrupted by external noise. This demands cutting-edge technology and innovative engineering solutions. It pushes the boundaries of our technological prowess. Researchers are developing new materials, error correction techniques, and cooling systems to keep qubits stable and functional. The race to build a practical quantum computer is a global effort, with scientists and engineers collaborating across borders. Yet the potential rewards are so significant that scientists and engineers around the world are racing to overcome these hurdles. The promise of quantum computing is too great to ignore, and the breakthroughs we achieve today will shape the technology of tomorrow. As we stand on the brink of this new era, the possibilities are as vast and exciting as the quantum world itself. To understand quantum computing, we must first venture into the heart of the quantum world. This is a realm that defies our everyday experiences and challenges our understanding of reality. It is a place where the rules of classical physics no longer apply, and the behavior of particles is governed by the strange and often counterintuitive laws of quantum mechanics. This is a place where particles can be in multiple states at once, a phenomenon known as superposition. In the quantum world, particles do not have a definite position or state until they are observed. Instead, they exist in a cloud of probabilities, occupying multiple states simultaneously. In this realm, information can be teleported across vast distances through a process called quantum teleportation. This is not the teleportation of science fiction, but rather the transfer of quantum information from one particle to another, instantaneously and without any physical travel. The very act of observation influences the outcome of an experiment in the quantum world. This is known as the observer effect, where the mere act of measuring a quantum system forces it into a definite state, collapsing its wave function. One of the most fundamental concepts in quantum mechanics is superposition. Imagine a coin spinning in the air, neither heads nor tails, but existing in both states simultaneously. This is the essence of superposition, the ability of a quantum system to exist in multiple states at the same time. When we think of a coin toss, we expect it to land on either heads or tails, but in the quantum world, the coin can be in a state of both heads and tails until it is observed. This duality is what makes quantum mechanics so fascinating and perplexing. Superposition allows quantum computers to perform complex calculations at speeds unimaginable with classical computers. By harnessing the power of particles in multiple states, quantum computers can solve problems that would take traditional computers millions of years to crack. Another mind-bending phenomenon is entanglement. This is a mysterious connection between particles that allows them to instantaneously affect each other, no matter how far apart they are. Imagine two coins, separated by a vast distance yet somehow linked. When you flip one coin and it lands on heads, the other coin instantly flips to tails, no matter how far apart they are. This is entanglement, a phenomenon that defies our classical understanding of space and time. Entanglement is not just a theoretical concept. It has been experimentally verified and is the basis for emerging technologies like quantum cryptography and quantum networks. These technologies promise to revolutionize communication and security by leveraging the unique properties of entangled particles. This is entanglement, the spooky action at a distance that baffled even Einstein. Despite his skepticism, entanglement has been confirmed by numerous experiments and is now a cornerstone of quantum mechanics. These are just a few glimpses into the strange and counterintuitive world of quantum mechanics. It is a world that challenges our perceptions and forces us to rethink the nature of reality itself. A world where our everyday intuition breaks down, and where the classical laws of physics give way to a new set of rules that govern the behavior of the smallest particles in the universe. In this quantum realm, the very nature of reality is called into question. It is a place where particles can be in multiple states, where information can be teleported, and where entangled particles can communicate instantaneously. The quantum world is a fascinating and mysterious place, full of potential and promise for the future of science and technology. In the digital world we know, information is stored and processed in bits. These bits are the smallest units of data in computing, forming the foundation upon which all digital information is built. A bit is a binary digit, representing either a 0 or a 1. This binary system is the language of computers, allowing them to perform complex calculations and store vast amounts of information. It's the fundamental unit of information in classical computers. Every piece of data, from a simple text file to a high-definition video, is ultimately broken down into bits. Like a light switch that can be either on or off, a bit can be either 0 or 1. This binary state is what makes digital technology so reliable and efficient. Quantum computers, however, rely on qubits. These are the quantum counterparts to classical bits and operate on entirely different principles. A qubit, or quantum bit, can exist in a superposition. This means it can be in a state of 0, 1, or both at the same time, thanks to the principles of quantum mechanics. It can be 0, 1, or both simultaneously. This unique property allows quantum computers to process information in ways that classical computers cannot. Think of a qubit as a dimmer switch, capable of existing in a spectrum of states between fully on and fully off. This analogy helps to understand the fluidity and flexibility of qubits. This fundamental difference between bits and qubits is what gives quantum computers their extraordinary power. They can solve problems that are currently intractable for classical computers. By harnessing the strangeness of superposition and entanglement, quantum computers can explore a vast number of possibilities simultaneously. This capability is what makes them so powerful and promising for the future of computing, leading to exponential speedups for certain types of calculations. This means that tasks which would take classical computers years to complete could be done in mere seconds by quantum computers. The potential applications are vast, from cryptography to drug discovery, and even to solving complex optimization problems. As we continue to develop and refine quantum computing technology, we are on the brink of a new era in information processing. The possibilities are endless, and the impact on our world could be profound. The journey from bits to qubits represents a monumental leap in our understanding and manipulation of information. It's an exciting time to be at the forefront of this technological revolution. As we unlock the secrets of quantum mechanics and apply them to computing, we are not just building more powerful machines, we are expanding the very boundaries of what is possible in the digital realm. The future of information technology is bright, and it all starts with understanding the building blocks of information. Section 4. Superposition. Embracing uncertainty. Imagine a maze with countless paths. A classical computer would have to explore each path one at a time until it found the exit. A quantum computer, on the other hand, could explore all paths simultaneously, leveraging the power of superposition. This is because a qubit in superposition is like a coin spinning in the air. It's in a state of uncertainty, existing in multiple states at once. It's not until we measure the qubit, forcing it to collapse into a definite state of 0 or 1, that the uncertainty is resolved. This ability to embrace uncertainty and explore multiple possibilities simultaneously is what makes quantum computers so powerful for certain types of problems. It's like having a massive parallel processing machine that can explore every possible solution at the same time. Section 5. Entanglement, a mysterious connection. Entanglement is one of the most bizarre and intriguing phenomena in quantum mechanics. It's a strange link between two or more qubits. It allows them to share a fate, no matter how far apart they are. Imagine two entangled qubits. If you measure one qubit and find it in a particular state, you instantly know the state of the other qubit, even if they are light years apart. It's as if the two qubits are connected by an invisible thread, sharing information instantaneously. This spooky action at a distance has profound implications for quantum computing. It allows us to create powerful correlations between qubits, enabling us to perform calculations in ways that are impossible with classical computers.